Hi, everyone. I'm Florian Tramer. I'd first like to thank the workshop organizers for this really nice award and for inviting me to give this talk today. So I very recently defended my PhD thesis on adversarial machine learning, and so I thought this could be a good opportunity to take a step back and reflect a bit on what we've achieved as a community over the past few years and where to go next. And so I gave my talk this somewhat ominous title: does adversarial machine learning research, this research that we're all doing and which is why we're here today, does it matter? One thing is undeniable is that adversarial machine learning research, and in particular attacking machine learning models, is very popular. There's a variety of attacks that have been proposed over the past years, such as evasion, poisoning, data inference, model stealing. And all of these have led to a huge amount of follow-up work on better attacks and defenses for machine learning. And yet, in this talk, I'm going to ask, well, does this research matter? So usually when one phrases a title as a question, that means that the answer is no. In journalism, there's actually a name for this. This is called the Betteridge law of headlines. And so today I'm actually going to defend this somewhat controversial take, I think, that this research we've done so far doesn't matter. And by that, I really don't mean to denigrate any of the research we've already done in this space, which I think is great and has given us a sense for how vulnerable machine learning models could be in principle. But I want to argue that we should try to go beyond that and really treat adversarial machine learning as a real security problem. So what does it mean to me to do real security research? I'm going to focus here on attacks in security research. So what does it mean to do a real attack? So to me, a cool security attack is one that takes a real system that people already use, or where there's compelling evidence that the system will be used by many people in the future. And the research then shows how to break this system. And ideally after that, we'd obviously also find ways to make the system better and safer. And so here are just some examples of my favorite security attacks from the past decade or so. I'm sure I'm missing a bunch of cool ones, so sorry if your favorite attack paper is not there. But even if you don't work in computer security, you've probably heard about some of these over the past few years, like the Heartbleed attack or Spectre. And really what all these attacks have in common is that they target a real system that's used by many, many people. For example, the authors of the Spectre paper, they didn't design their own hardware that's sort of maybe roughly like a real Intel processor. No, they took a real Intel processor and attacked exactly that. And in the same way, Heartbleed wasn't an attack on a protocol that's a bit like TLS. No, it was an attack on the actual TLS protocol as implemented in OpenSSL and used in millions of websites. And I have to say here that not all of these attacks are necessarily super practical. Many of them are actually really hard to pull off, but still they all target a real system. And I argue that we do not yet have many examples of such attacks in the adversarial machine learning literature, because what we're missing is this crucial first step where we actually target a real security system and not some artificial system that we've come up with for research purposes. And this means that despite all this attack research we've done so far, it's actually pretty hard to say whether we could use these techniques we've developed to attack a real security sensitive model. So consider, for example, YouTube's content filtering system that tries to detect when people upload videos that shouldn't be on YouTube and removes them. As far as I know, no one's actually demonstrated how to principally evade a system like this using adversarial machine learning. The same goes for poisoning attacks. So for example, how would one go about poisoning this same YouTube model so they would just block all of Justin Bieber's videos? This is a bit of a stupid example, of course, but still, it would be a real attack on a real system. We can ask the same questions about privacy. Like, could we mount an attack on an actual production system to extract real user data? And we could wonder the same thing for model stealing. Like, would it be possible to steal a proprietary model like GPT-3 in order to just be able to use it without having to pay for queries. And this research on real attacks that I think is currently missing really matters. Because as we'll see, our current attack techniques are not actually very well suited for attacking such real systems. And so it's not clear whether we might sometimes be making a fuss for nothing with some of these attacks. Maybe it's actually really hard to pull an attack off in reality. And so we might not actually need to invest so much time looking for perfect defenses because the attacks aren't actually feasible. It's also possible that attacking these real systems does work, but then it probably requires a bunch of additional tricks than what we currently see in our research. And this in turn might mean that there could be some pragmatic ways of designing defenses that might not work when you consider machine learning models in isolation, but that are helpful in the context of a real system. And these are really the types of questions that I think are largely not addressed by our current research and would be really, really interesting to explore. So I'm now going to illustrate this gap between research attacks and real-world attacks for these 4 specific classes of attacks on machine learning systems. I'll focus mainly on evasion attacks and poisoning attacks, and briefly talk about data inference and model stealing towards the end. So let's start with evasion attacks. So basically, the question I'm interested in here is how we go from the types of attacks that we currently focus in academic research, like this picture here on the left with the panda that's transformed into a gibbon with a small perturbation, how we go from this to a real evasion attack on a real security system that services billions of users. And this is actually quite hard to do because research on adversarial examples, sort of for better or worse, tends to focus on a very specific attacker model. So I would estimate that about 95% of papers or so on this subject consider these kind of imperceptible pixel level perturbations like the panda on the previous slide in a setting where the attacker has complete access to the model. This is what we call a white box attack. And then there's a much smaller number of papers, maybe 5% or so, that look at black box attacks where the attacker can only interact with the victim model via some query interface. And then there's maybe a very small fraction, less than 1% of papers that consider the sort of fully black box setting where you might not even get to reliably query the model. Now, if we look at real machine learning systems, it's kind of the exact opposite. So I would guess that 99% of those systems are actually complete black boxes to which you typically don't get direct query access. And on top of this, for most of these systems, there are going to be viable attacks that are not necessarily imperceptible. And so there's kind of a clear gap between the goals here. And so the question is how we could reconnect these two, how we could go from what we've been studying in research to real systems. And so one option would be to look for a real security system where the attacker can have white box access and where imperceptible perturbations matter. So that means sort of taking the things we know how to do in research, sort of taking this hammer and sort of trying to find a nail somewhere in the real world that actually applies. And this is what my co-authors and I did 2 years ago when we demonstrated adversarial examples against machine learning-based ad blockers. And ad blockers are actually quite peculiar as far as security systems go because they operate client-side. And so it's very hard to hide the model from the attacker. The attacker can just go and download the same ad blocker as all the other users use and then look at how it works. And so here we are really in a white box setting. And another peculiarity of ad blocking is that there's always a human involved because the goal of the attacker here is to evade the automated blocking system, a machine learning model, to ultimately show ads to an end user. And so imperceptibility of attacks kind of matters here. And so what we showed in this research was that these kind of attacks that we've developed in a research context for evading machine learning models, they perfectly apply to this setting and make this use of machine learning for ad blocking really hard to pull off. And still, I would say that here, the setting that we considered was still somewhat artificial because no one's actually using machine learning for ad blocking today. There have been some proposals to do this, but we didn't get to attack any real systems in this paper because they don't actually exist yet. And we believe that they might at some point, and that if that were to happen, well, these systems would be threatened by adversarial examples. And so the other direction, the more natural direction we should maybe go for here would be to first take a real system. So again, think of something like YouTube's content filtering, and then see what it would take to attack a system like this. And I claim that this is really more than just an engineering exercise, because the system's a complete black box. You don't know what kind of techniques exactly are being used. You can't directly query the system either. I mean, of course, you could try to upload videos to YouTube and then see if they get taken down or not. But if you do this a few times and the video actually gets taken down, at some point your account is just going to get locked, and then you're going to have difficulty building a new account and so on. So you might then also think of doing some kind of transfer-based attack, but here it's also not very clear how you would build a good surrogate model for yourself. And so the kind of attacks that we've studied in the academic literature, it's not completely clear to me how to best apply them to such a real-world setting. So showing how to systematically attack such a system is, I think, a really cool research direction to go for. So I want to highlight that there are a few works already that try to do things like this. So there's been, for example, some attempts at using transfer attacks against porn filters. There was this interesting paper a couple of years ago at Oakland. There was also a recent paper on attacking copyright detectors using adversarial examples. These attacks are still quite far from as good as what we've come to expect from white box attacks. And so it's really interesting to see how far you could go with a practical attack on these systems. There's also some cool stuff happening on this front from industry. So there's this adversarial threat matrix project that compiles sort of known incidents of machine learning attacks on real systems. That's very cool to look at for inspiration for research. There's also an ongoing competition sponsored by Microsoft for building realistic adversarial malware and building defenses. And so this is also worth looking at if you're interested in these sort of real world attacks. I think there's also quite a lot of interesting research questions here on the side of defenses for real systems. Because the attacks faced by these systems are presumably going to be quite different in nature from your sort of standard worst case white box attacks, the type of defenses you'd likely deploy in production are also going to be very different from the ones we've seen in the academic research so far. And I think there's just not a lot of research yet on what we should be doing on this front. So to conclude on this topic of evasion attacks, I wanted to highlight one specific recent example that I think very clearly illustrates this gap between research and practice. So you've probably heard of Apple's recent announcement that it was going to start scanning pictures of child abuse material on phones. And basically, the way this works is that they run your images through a machine learning model to compute a fingerprint or hash, and they then compare this hash to a database of known pictures of abuse. Of course, the goal of this hash is that it should be robust to small changes in images so that you can just easily evade detection by changing images slightly. And Apple's announcement started a big controversy around data privacy, but there were also questions about how robust this system would really be to attacks. And so people say on Twitter, like Matt Green, who's a famous security researcher, were kind of asking like the people from the adversarial machine learning community to weigh in here and say like, would this really work? And it worries me a bit that despite the fact that we've written thousands of papers on adversarial examples at this point, it's actually really hard, I think, to give a proper answer to this question, because I'm fairly certain that Apple's machine learning model that they use for this image hashing is not robust to white box attacks. I would be very surprised if they've solved adversarial examples somehow. But does this necessarily mean that there's an actual practical attack one could launch against this model if it's just a black box? It's kind of hard to say. And that's why I think we need more research on trying to attack real systems so we get a better sense of how feasible this actually is in practice. Let's now move on and talk about a different class of attacks, namely poisoning attacks. There's maybe not been 1,000 papers on this topic just yet, but certainly hundreds. on how you can tamper with a model's training data to cause it to misbehave. And so you could wonder then, well, why didn't anyone actually demonstrate a poisoning attack against some recent models, like say GPT-2 or GPT-3 or GitHub's recent Copilot model that were all trained on just publicly available data? And we certainly believe that such attacks would be feasible. And there's been a bunch of research papers sort of arguing that this would be possible. And yet again, I think we would learn a lot from just going and actually trying to run such an attack in a real world scenario, where you typically don't know a priori what kind of model is going to be trained on your data and how. And so it would be really interesting to see exactly how this would work and how well it would work. There's actually one specific attempt at poisoning real-world systems that I know of and that I want to discuss here, because again, I think it nicely shows how careful you have to be when moving from a research attack environment to attacking a real system. This example deals with facial recognition systems. So you might have heard of Clearview.ai, a company that made headlines a few years ago because they trained large-scale facial recognition systems by scraping public pictures from the web, and they then sold the system to law enforcement agencies. And so some researchers from the University of Chicago originally proposed this neat idea: why wouldn't we just poison these systems? And the way this would work is that whenever we upload a picture online, we would first perturb it using an adversarial example. And these pictures would then be scraped and collected by Clearview to train a model. But the hope would be that when the model is then asked to identify a clean picture of you, say one that was taken by the police at a government protest, the model would then fail to recognize you because it sort of learned to identify you only with these adversarial examples of yourself. And the reason we'd want adversarial examples here is because we actually want the pictures that we upload online to still look like us so that we can share them with friends, with family, and so on. And so this was a real attempt at attacking real systems, because these researchers actually built a workable tool out of this idea, and this got a huge amount of publicity, and their tool has been downloaded over 500,000 times apparently. And this has also prompted a bunch of follow-up work by other researchers who have proposed similar poisoning attacks aimed at real facial recognition systems. But recently, with Ivani Radyadixit, who's an undergrad at Stanford, we wrote a paper arguing that these attacks weren't actually ready for real-world deployment, and that they were luring users into a false sense of privacy. And the core issue that we identified here is what we call retroactive defenses against poisoning. Basically, what we believe Clearview could do is to collect a bunch of pictures today by scraping the web. And these pictures might have been perturbed using today's best poisoning attacks. And then they could just wait 1 year and take whatever the state-of-the-art machine learning model is then and train that model on the data that they collected a year before. And so what this means is that if you want your poisoning attack to be effective, you somehow need to anticipate future advances in machine learning and sort of ensure that the attack transfers to all of these future models as well. And this isn't something that current research on attacks actually aims for. And we show in our paper that current attacks are very unlikely to succeed in staying effective into the future as is required. This idea of a retroactive defense against data poisoning is quite simple. And it's a defense that actually only really makes sense when you think of the long-term dynamics of a machine learning system. And in contrast, most research on poisoning attacks and defenses tends to consider a sort of a closed world scenario where there's one training set and the model gets trained on it once and then it gets evaluated once, as we kind of tend to do in academic research. And this has sort of led to the design of much more complicated defenses, both heuristic and provable ones, with just some examples illustrated here. One of these is actually from one of my own papers from a few years ago. And so I think it's worth thinking about what kind of other pragmatic defense strategies might exist if we think outside of this closed world setting and really consider how a machine learning system evolves dynamically in the real world. So for example, here's a really simple yet incredibly strong heuristic baseline defense against data poisoning. If you want to make sure your model is safe from data poisoning, just train your model only on data collected, say, before 2018, which is when the first poisoning attacks on deep learning systems were proposed in academic papers. Now, this defense is not always going to be applicable, of course. For many applications, you actually need to continuously update your model with new data. But I think it goes to show that the design space for defenses of real systems can be much broader than what we may consider in sort of closed world research experiments. And so again, here, I think there's a lot of research opportunities for bridging this gap between poisoning attacks in research and in the real world. I think it's worth trying to better understand the actual threat model for poisoning attacks on real world systems, because the attack dynamics here seem to be quite delicate, especially when we consider models that can be dynamic and retrained over time. And as for evasion attacks, there are little to no examples as of yet of an actual successful poisoning attack against a real system. And this is definitely something worth exploring more. And finally, as we just saw, there seemed to be an interesting design space here for real world defenses against poisoning attacks as well. Let me now move briefly to data inference and model stealing before concluding my talk. So data inference is actually the setting where I think I'll have the least to say, because here I think that the threats identified in academic research can actually be quite close to the threats that a real system would face. So one of the clearest threats we've identified, for example, is that generative text models can memorize snippets of training data and output them when given some random prompt. So the model can just sort of leak data that it's been trained on. And as an attacker, you don't even have to do much. You just need sort of the ability to run the model. And here, this is getting much closer to what I'd call an attack on a real system, because of course, GPT-2, which we looked at in this research paper that appeared at Usenix Security, is still very much a research model. But the attack principles here are completely black box and presumably apply to any large language model. And it turns out that these issues are starting to be discovered in models put into production. So for example, there was a Korean messaging app that used private data that it collected from users to build an AI chatbot. And people then figured out that this AI chatbot could be made to leak private information from its training data. And so this was really a real model trained with real user data that started having this issue. And so this is really not just a research consideration anymore. It's really something that people have to think about and care about when they put models into production. And so I think it's likely that we're going to see similar data leaks happening elsewhere unless companies become very careful in how they train their models and release them. So here, I think it would be very interesting to see if similar extraction attacks could also work for other types of data than just text, which is kind of what's mainly been shown so far. So for example, could you do this with images or with speech and so on? And of course, there's the big open question here about how to prevent such data leaks effectively. So differential privacy is often suggested as the ultimate solution here, but it's currently quite hard to apply at scale for these huge models. And so there might be some other effective defense strategies that are possible here, especially again, once you think in terms of a real security system that might be able to, say, monitor the type of queries that it receives from users and so on. Okay, so that's all I wanted to say about data inference. So let's now conclude by talking about model stealing. And I would say that out of the 4 types of attacks that we've discussed here, model stealing is probably the one where we face the biggest hurdles towards seeing a practical attack. Because actually, even in research settings, copying a model's functionality is still quite hard to do. So even in sort of research settings, I don't think we've really yet managed to pull off particularly compelling attacks. So when we wrote this original paper on model stealing 5 years ago, the threat we considered was that you could undermine a pay-per-use API by querying some black box model, say in the cloud, a bunch of times. And so you would have to pay for those queries. But then you would just locally reproduce the model and from there on stop paying for queries. And the principle that's being exploited here in this attack is basically model distillation. So if you can query the API to get some richer information than just labels, say for every query you send to the server, you get back the model's internal representations for this input, then empirically we know that you can actually replicate the model quite efficiently. But so it's interesting to consider how feasible this would really be for a real production system. So we could look at, say, GPT-3, where we have a reasonable understanding of the different costs involved, and this model really is currently private. You can only query it through OpenAI's paid-for API. And so we can do some calculations here. Like, it's estimated that to replicate GPT-3 yourself by just retraining the model from scratch, because all of the training data is public here, this would cost somewhere around $5 million in cloud GPU costs. It's like very expensive to train this model. And so you could ask then, well, could we reduce this cost by somehow leveraging the fact that we can query GPT-3 and sort of use this to do some kind of model distillation? But querying GPT-3 is actually quite expensive. So you need to pay about $3 million to obtain GPT-3's internal representations for just 10% of its original training data. And so let's say you did this, then you'd still have to pay for the costs of training your local model with some form of model distillation. And so overall, it's not clear to me here whether a cost-effective model stealing attack would be possible or not. And I'm not suggesting that someone should try this because it seems like it's too expensive, but it's kind of interesting to consider what the economics of these kind of attacks really are and sort of when such a distillation-based attack might be feasible or not. So as I said, yeah, here I think we have quite a gap to close between model stealing as a research problem and an actual practical attack vector. First, I think there's a lot of unexplored territory here, even from a research setting. I would say that compared to the other classes of attacks we've discussed before, evasion, poisoning, and data inference, I would guess that model stealing has comparatively received a lot less attention. So we have a much lower understanding of sort of what is feasible in terms of attacks here. And if we were to actually find good attacks that work well in a research setting, then again, it's worth finding out how well these attacks would really work in practice and sort of at what kind of query prizes model extraction might become economically viable. So with this, I'll conclude my talk by reiterating that there's been a lot of very cool research on adversarial machine learning so far, from which we've learned that in principle, any model can be attacked, and if you give the adversary enough access. And that it's very, very hard to prevent these kind of strongest possible attacks that we've discovered. And this gives us an upper bound on how vulnerable machine learning systems can be. But I claim that we don't really know yet how tight this upper bound really is, because these strong attacks that we've developed in our research aren't really realistic in the vast majority of practical settings. Like, you're never going to get white box access to a model, for instance. And so there remains a big open question of what real attacks and defenses on real machine learning systems should look like. And I really hope that our field can answer some of these questions over the next few years so we can get a better understanding of what machine learning security really looks like in the real world and how safe users of these systems are. Thank you.